Welcome to iLecture Online, and here's our next lesson in how to integrate. And here we're going to use a very useful method called the integration by substitution. And this is actually a very wide-ranging method that can be used in all kinds of circumstances, all kinds of cases. Very fundamental to integration, and so we're going to see a lot of examples here. The concept is very simple. So if we have something that looks like this, in order to integrate this, we have to have what we call the proper differential. And in order to understand how to get that, we use a method called the method of substitution. We're going to go ahead and take what's inside the parentheses here and substitute that for another variable. Let's say the variable u. So we're going to say let u equal what's inside the parentheses. So this is 3x minus 8. And then we're going to take the derivative of u with respect to x. So the next step is take the du dx, and the du dx of 3x minus 8 is equal to simply 3. Then we cross multiply the dx over here, so say du is equal to 3 dx. And then if we solve this for dx, we can say that dx is equal to du divided by 3. And now what we're going to do is we're going to substitute this in for 3x minus 8, and we're going to substitute this for dx. And when we do that, we get the following, right? So this becomes the integral of 5 times, instead of 3x minus 8, we're going to write u to the 4th power. Instead of dx, we're going to write du over 3. Then the next step, we're going to take the 5, take it outside integral sign, and divide by 3 takes outside integral sign. So this can now be written as 5 over 3 times the integral of u to the 4th du. And now you can see that this is a nice, simple, easy format that you know how to integrate. So let's do the integral. So this is equal to 5 over 3 times u to the 5th power over 5 plus a constant of integration. We can see that the 5's cancel out, and so this can now be written as 1 over 3 u to the 5th plus a constant of integration. Well, now we're not done yet, because now we want to substitute back what u was equal to in terms of x. So let's replace u by 3x minus 8. And so we now can say that this is equal to 1/3 times u to the 5th, and u is 3x minus 8. So we can write 3x minus 8 to the 5th power plus a constant of integration. And that here is the integrated form of the integral that you see up here. And this method is therefore a really useful method, because if you don't have the proper differential here, by using the method of substitution, you can find the proper differential and then integrate it and substitute back and get the right answer like that. Okay, so if this was kind of bewildering, stay put. I have a lot more examples to come, and after a while you say, oh, okay, I can see the technique. That seems to be pretty straightforward. So let me show you all kinds of different ways in which the method of substitution can be used. Here's our second example of how to use the method of substitution to integrate something that looks like this. And right away you realize here that we don't have the proper differential. So we're going to take what's inside the parentheses and substitute that for the variable u. So let u equal what's inside the parentheses. That's usually a good rule of thumb to do that. So we write 3x squared plus 3. And then we take the derivative with respect to x. So du dx is equal to 3x, because we multiply the exponent times 3. So this gives me 6x. And then we multiply the dx over there. So du is equal to 6x dx. And then we solve that for dx. So dx is equal to du over 6x. And then we substitute this and this into our integral. And let's see what happens when we do that. So this becomes the integral of 2x divided by, this now becomes u, so u to the 5th power, and dx can now be replaced by du over 6x. And notice that this x and this x cancel. That was the whole object of doing that. And then 2 divided by 6 is 1/3, which can be taken outside integral sign. So this is equal to 1/3 times the integral of 1 over u to the 5th du. And then, of course, when you have 1 over u to the 5th, what you're going to do is you're going to move this to the numerator and turn this into a negative exponent. So this is equal to 1/3 times the integral of u to the minus 5 du. And that you know how to integrate, because you simply use the power rule. So this is equal to 1/3 times u to the minus 5 plus 1. We add 1 to the exponent and divide this whole thing by the new exponent, minus 5 plus 1. Okay, and don't forget the constant of integration plus c. And then if you simplify that, so this is equal to 1/3 times u to the minus 4 divided by minus 4 plus the constant of integration. Don't forget that. So now we're going to take 1/3 divided by -4. That's 1 over -12. And u to the minus 4 can then be written as 1 over u to the 4th. So this is equal to 1 over -12 times 1 over u to the 4th and plus a constant of integration. And then finally what we can do is now replace u by what u is equal to in terms of x. And so this can now be written as 1 over -12. And instead of u to the 4th, we write 3x squared plus 3 to the 4th power plus a constant of integration. And that's the integral of this initial problem. All right, so that looks a little complicated, but again, the steps are, you see an integral there. You don't know how to integrate this because you don't have a proper differential, dx. Actually, the way you look at it is you need a 6x dx here in order to integrate that. Since you don't have that, you use the method of substitution. You let u be what's inside the parentheses. You take the derivative with respect to x, then you solve for du, and then you solve for dx, and then you substitute what's here and what's here back in integral. It looks like this now. The object is to get rid of these x's, so the x's disappear. The 2 over 6 is 1/3, comes outside the integral sign. Now you have 1 over u to the 5th du. To integrate it, you want to move it to the numerator with a negative exponent. Then you simply use the power rule, and then you substitute back in what u is equal to get the final answer in terms of x. All right, that's how you do that one. And many more examples to come if you want to see some. And here's our third example of how to do integration using the method of substitution. And here's something that when you first look at it, you go, wow, how do you integrate that? Well, here's the trick. First of all, when you have a radical like this, let's get rid of the radical and write it like this. This is equal to the integral of 3y squared times the quantity y cubed minus 1 to the 1/2 power dy. Now, if you have a little bit of insight, after you do this for a while, and you see what's inside the parentheses here, and it's raised to the 1/2 power. If you take the derivative of what's inside the parentheses, you get 3y squared, and notice there's a 3y squared here, and you have a dy there. So this is really the differential of what's inside the parentheses. Since you probably are not quite that comfortable yet with that, you say, okay, that may be true, but let's use the method of substitution, and when we do that, you'll find out that the 3y squared dy will disappear, and you can then easily integrate what's left. And so that's how I illustrate why this is the proper differential of what you need here. So we're going to use a substitution. Let u equal what's inside the parentheses, which is y cubed minus 1, and then the derivative of that with respect to x. Oh, not with respect to x because I'm using the variable y here. Okay, that works. It doesn't matter, x, y, z. In this case, it's a y, so du dy is equal to 3y squared. Multiplying the dy over here, we get du is equal to 3y squared dy. And finally, we can say that dy is equal to du divided by 3y squared. And we're going to substitute this and this back in the integral and see what we get. So this is equal to the integral of 3y squared times, instead of writing y cubed minus 1, we'll write u to the 1/2 power. And instead of dy, we'll write du divided by 3y squared. And just as I predicted, the 3y squared in the numerator will cancel out with the 3y squared in the denominator, disappears, and then we're simply left with the integral of u to the 1/2 power du. All right? So sometimes, without going through these steps here, you can look at this and go, the derivative of y cubed minus 1 is 3y squared, and then the differential is dy. So since I have a 3y squared dy, I can simply integrate what's there. But again, if that doesn't feel comfortable, or you say, I don't quite understand that, it's perfectly okay to go ahead through these steps and simply use the method of substitution. And then you end up with something like this, which is really easy to integrate. So this is equal to u to the 1/2 plus 1, which is 3/2 power, right? 1/2 plus 1 is 3/2, divided by the new exponent, 3/2 plus a constant of integration. Of course, divided by 3/2 is the same as multiplying times 2/3. So this is equal to 2/3 times u to the 3/2 plus a constant of integration. And then all we have to do at this point is simply substitute back in what u is equal to in terms of y. And so this can be written as 2/3 the quantity y cubed minus 1 to the 3/2 power plus a constant of integration. And that is the integral of what we started with over here. Here's example number 4, how to do integration using the method of substitution. And here we have, of course, the exponential form e to the x, or in this case, e to the x cubed plus 1. And again, what you do here in this case is you take the exponent of e to the x cubed plus 1 and substitute that for u. So you let u equal x cubed plus 1. Therefore, du dx will be equal to 3x squared, and du will be equal to 3x squared dx. And solving this for dx, you get dx is equal to du divided by 3x squared, and then you substitute this and this inside the integral sign. All right, so that's the standard format. That's how you do everything. And then when you substitute back in, what do you get? So this is equal to the integral of x squared times e to the, instead of x cubed plus 1, you write u. And instead of dx, you write du divided by 3x squared. And then notice this x squared cancels out with this x squared, and all you have then e to the u du divided by 3. Then, of course, you can take the 1 over 3 outside integral sign, so this becomes 1 over 3 times the integral of e to the u du, and that's a very classic form, e to the u du. The integral of that, of course, is simply e to the u, and of course, don't forget the constant of integration. So this is equal to 1/3 e to the u plus c. And then you substitute back in what u is equal to in terms of x. So this is equal to 1/3 e to the x cubed plus 1 plus a constant of integration. And that's the final form of the answer of the integral of x squared e to the x cubed plus 1 dx. So even though it looks kind of mean and ugly when you start out like this, when you substitute in for u, then it becomes a pretty easy integral. Here's our 5th example of how to use the method of substitution for integration. And here it is, the natural log, the integral of the natural log of 3x over x dx. Here you say, wow, what do I do with this thing? Well, let me show you a hint here. I'm going to separate this a little bit and write it as the integral of the natural log of 3x times 1 over x dx. And then I'm going to take this here and substitute that for u. So let u equal the natural log of 3x. So du dx, the derivative of that is equal to 1 over 3x. Oh, I say du dx, and I write du. That doesn't work. Du dx is equal to 1 over 3x. And so then I can say that du is equal to 1 over 3x times dx. And then finally, dx is equal to 3x times du. And then we can substitute this and this inside our integral sign. So let's see what we end up with. So the natural log of 3x can be replaced by u. So this is equal to the integral of u. And 1 over x dx, let's see here, the dx can be replaced by 3x du. So times 1 over x, and dx is 3x times du. And then you can see that this x and this x cancels out. And you end up with the integral of u times 3 du. And then, of course, you want to take the 3, which is a constant outside integral sign. So this is equal to 3 times the integral of u du. And that, of course, can be integrated. This is equal to 3 times u squared over 2, right? Raise the 1 to the exponent, divide by the new exponent. And then, of course, plus a constant of integration. And finally, replace back for u what u is equal to, which was the natural log of 3x. So this is equal to 3 times the natural log of 3x, quantity squared, divided by 2, plus a constant of integration. There we go. And that's the answer. Now you say, wow, how in the world would I have figured this out? Well, sometimes you just kind of have to guess. So maybe you say, okay, I'm going to replace 1 over x by u, so substitute that way. And when you try that, it probably won't work. And then say, well, maybe I'll substitute x for u and try that, and that probably won't work. Maybe you'll substitute 3x for u, and that won't work. So sometimes you try different things. But in this case, if you let the natural log of 3x equal u, and you can then see, then it works out, and you can solve the problem. So sometimes it's kind of a hit and miss. You may not know exactly what to substitute, but here's the example, and I recommend when you see something like this, take the whole natural log of 3x and make that equal to u, and as you can see, then you can solve the problem. Here's our next example of how to use the method of substitution to do integration, and this is kind of a classic example. If you have never been shown how to do this problem, as simple as it may look, this is actually a kind of a difficult problem, and you may not be able to figure it out on your own. It may take you a while. So look carefully, see what I do. So we need to substitute something here, and I'm going to take a guess. I'm going to say let x plus 1 equal u. So let u equal x plus 1, which means du dx is equal to 1, and du is equal to dx, or dx is equal to du, which means I'm going to substitute this and this back inside the integral sign and see what we end up with. So this is equal to the integral sign of x divided by u, and instead of dx, we write du. Now you look at that and go, whoa, I'm in trouble. I can't integrate that. I can't have more than one variable inside my integral sign. Well, the trick is to go back over here and say, well, if u is equal to x plus 1, this means that x is equal to u minus 1. And so we're going to then substitute this x up here by u minus 1. And so this can now be written as the integral of u minus 1 over u times du. And now you can divide the denominator into the numerator. So if you do that, this is equal to the integral of u divided by u is 1 minus 1 over u du. And this is kind of like a polynomial. We can then separate that into two integrals. So this can be written as the integral of 1 du minus the integral of 1 over u du. All right? So once you have it like that, now you can integrate both of these integrals. The integral of 1 du is simply u. So this is equal to u minus. And the integral of 1 over u du, that's the classic case. That's, of course, the natural log of u. And, of course, don't forget the constant of integration. And then you substitute back in what u is equal to here and here. So this is equal to u, which is x plus 1, minus the natural log of, instead of u, you write x plus 1, and don't forget the absolute value signs, and then, of course, plus the constant of integration. And this here is the integral of that form. And again, if you've never seen this worked out before like this, you probably won't think about it. And this is a good thing to memorize. So again, first you just let u equal x plus 1. That means that dx equals du. You make the substitution. You still have an x in there. Now you have to get rid of that x. The clever way is to then go up here and solve this equation for x and substitute for x u minus 1 right here. And then you still can't quite integrate it. But then if you realize if you divide the denominator into the numerator, you end up with something you can integrate. And then you're on your way to solve it. And that's how you do that particular problem. Example number 7 here to illustrate how to integrate using the method of substitution is kind of a classical example. What you may not realize when you first look at this is that this quantity right here, the 6x squared minus 1 times dx, is the exact differential of this part of the integral, which means you simply integrate this and this becomes this to the 5th power divided by 5 plus c. But you may not see that. And so using the method of substitution is kind of a quick, easy way to verify that. So we're going to let u equal, standard, the quantity inside the parentheses here. So it's going to be 2x cubed minus x, which means that du dx is equal to 6x squared minus 1. Therefore, du is equal to 6x squared minus 1 dx. And that means that dx is equal to du divided by 6x squared minus 1. And then we're going to substitute this and this inside the integral sign. So let's do that and see what we end up with. This is therefore equal to the integral of, this is now going to become u to the 4th power, and times 6x squared minus 1, and dx can be written as du divided by, right here, 6x squared minus 1. And now notice that this 6x squared cancels out this x squared minus 1, and this becomes the integral of u to the 4th du, and that's then easy to integrate. So this now integrated becomes u to the 5th over 5 plus a constant of integration, and then substitute back in what u is equal to right there. So this is equal to the quantity 2x cubed minus x to the 5th power divided by 5 plus a constant of integration. So there is a good way to illustrate that this quantity right here was the exact differential of this. So this could be written as u to the fourth du, and there's the integral. Here's example number 8 on how to use the method of substitution to integrate. Here's the example. You have a radical. It's in the denominator. What do? Well, let's first of all rewrite this. So this can be written as the integral of x squared divided by the quantity x cubed plus 3 to the 1/2 power times dx. And then you're going to take what's inside the parentheses and substitute that for u. So you're going to let u equal x cubed plus 3, which means that du dx is equal to 3x squared, and du then becomes 3x squared dx, and therefore dx is equal to du divided by 3x squared. And then you substitute this and this inside the integral. All right, doing that, this is equal to the integral of x squared divided by this quantity here now becomes u to the 1/2 power, and instead of dx, we write du divided by 3x squared. All right, now you see an x squared in the numerator and x squared in the denominator. That cancels out, and you have a 1/3, which can go outside the integral sign, and u to the 1/2 power in the denominator, that can move to the numerator and become u to the minus 1/2. So this now can be written as 1/3 times the integral of u to the minus 1/2 du, and this can be integrated using the method that we've learned before. So simply here we raise the exponent by 1, divide by the new exponent, so this is equal to 1/3 times u to the minus 1/2 plus 1 divided by minus 1/2 plus 1 plus a constant of integration. So I wrote it like that because sometimes it's a little confusing adding negative 1/2 to plus 1, but negative 1/2 plus 1, that gives me a positive 1/2. So this can now be written as 1/3 times u to the positive 1/2 divided by negative 1/2 plus 1 is a positive 1/2 plus a constant of integration. And then, of course, dividing by a fraction is the same as multiplying by its inverse. So this then becomes 2/3 times u to the 1/2 power plus a constant of integration. And then finally, we substitute back in what u is equal to, which is this right here. So this becomes 2/3 times the quantity x cubed plus 3 to the 1/2 power plus a constant of integration. And that's the integral of our original problem here. And again, the question is, if we're going to use the method of substitution, what is the substitution here? What are we going to substitute for u? And typically, the exponent of e is a good candidate. So let's try that. Let u equal minus 1/x. That means that du is equal to, how do we write that? Well, that's the derivative of that, so let's write this as minus 1x to the minus 1 power. And if we take the derivative of that, du dx, that's equal to, bring the exponent to the front, so that would be plus 1 times x to the minus 2, because then we subtract 1 from the exponent. Okay, and so that means that du is equal to x to the minus 2 dx, which can be written as du is equal to 1/x squared dx. And that means that dx can be written as x squared du. And then we're going to substitute this and this in the integral sign. All right. So instead of writing minus 1/x, we're going to write u. And instead of dx, we're going to write x squared du. So this can now be written as the integral of e to the u divided by x squared. And instead of dx, we write x squared du. And then notice that this x squared cancels out that x squared, and we simply end up with e to the u du. All right, so the trick here was take what the exponent is for e and replace that by u, and then you can see that the problem simplifies to a form that's easily to integrate, because e to the u du is e to the u, plus, of course, a constant of integration, and then you substitute back in what u is equal to, which is minus 1/x. So this is equal to e to the minus 1/x plus a constant of integration, and there's the integral, or the result of the integration as the example. And here's our 10th example of how to use the method of substitution to integrate. Now, if we take a look at what's inside the parentheses here in the denominator, and then you look at the numerator, this happens to be the exact derivative of what's inside here. That's why we can find the proper differential to integrate this. So what we're going to do is we're going to substitute what's inside the parentheses here for u, and then everything will just fall together. All right, so we have let u equal e to the x plus e to the minus x. If we do that, then du dx will become e to the x, because the derivative of e to the x is e to the x. And then the derivative of e to the minus x is e to the minus x times the derivative of minus x, which is minus 1, which means that it is equal to minus e to the minus x. And then du is equal to e to the x minus e to the minus x dx, or dx can now be written as du divided by e to the x minus e to the minus x. All right, we're going to then substitute this and this inside the integral. And if we do that, this now becomes the integral of e to the x minus e to the minus x, that's still the numerator, divided by this quantity, which now has become u, so u to the 5/2. And then dx is going to be substituted by du over this, du over e to the x minus e to the minus x. And then notice that this and this is exactly the same, so this numerator here cancels out that part of the denominator, and we now have the integral of, well, u to the 5/2 in the denominator can move to the numerator as u to the minus 5/2 times du, and this I know how to integrate. So then we integrate. This is u to the minus 5 over 2 plus 1 divided by minus 5 over 2 plus 1, plus a constant of integration, of course. And minus 5/2 plus 1 is minus 3/2. So this is equal to u to the minus 3/2 divided by minus 3/2 plus c. And of course, dividing by a fraction, same as multiplying by its inverse. So this is equal to minus 2/3 times u, not e, u to the minus 3/2 power plus c. And then finally, we substitute back in what u is equal to, which is this right there. So this is equal to minus 2/3 times u, which is e to the x, plus e to the minus x, to the minus 3/2 power plus c. And then of course, since it's a negative exponent, you may want to write that then in the denominator, and you can then say this is equal to minus 2 divided by 3 times e to the x plus e to the minus x to the positive 3/2 power plus c. So simply taking this quantity, writing it in the denominator with a positive exponent, and the minus 2 at the top and the 3 in the bottom. And that's then the final form of the answer, the integral of this right here. Okay, so again, sometimes by looking at it, and again, the hint would be that if something is inside parentheses raised to a power, this probably is the right candidate to be substituted for u. And so that's probably a good way to go. Example number 11 on how to do integration using the method of substitution. And this particular one, this problem, as simple as it seems, is actually quite a complicated problem to do, and a very good example of sometimes it's not so straightforward to use the method of substitution. But you can indeed integrate this going to the right algebraic steps. So let's start. We're going to let u equal the denominator, the square root of x minus 1. And instead of writing the square root, let's just use the exponent. So we're going to let u equal x to the 1/2 minus 1. Okay, and then what we're going to do is we're going to solve this for x to the 1/2. So x to the 1/2, and I write 2 when I say 1/2, so x to the 1/2 is equal to u plus 1 by moving the 1 over to the other side and moving the equation around. And then, of course, we also need to solve for dx. So if u is equal to this, then we can say du dx is equal to 1/2 x to the minus 1/2 power, which means that this is equal to 1/2 times 1 over x to the 1/2 power, which means that du is equal to 1 over 2x to the 1/2 times dx, or dx can be written as 2x to the 1/2 power du. So we're going to substitute this and this back in the original integral. Right? Let's do that. So this is equal to the integral of x plus 1 over u, and instead of dx we can write 2x to the 1/2 du. All right, we still have a ways to go because I'm trying to just only have u's in the integral and have an x plus 1 here and a 2x to the 1/2 power. But notice what I just did. I wrote x to the 1/2 equals u plus 1, so we can actually substitute x to the 1/2 power by u plus 1 and take the 2 and move it outside the integral sign. So this is equal to 2 times the integral of x plus 1 divided by u, and then instead of x to the 1/2 I can write u plus 1 du. All right, that at least puts us one step closer to being able to integrate this. But I still have the x plus 1 there. I need to get rid of that somehow. So if x to the 1/2 is u plus 1, then if I square both sides, I can then replace x by something in terms of u. So what I'm going to do here is I'm going to square both sides, and that means x is equal to u plus 1 quantity squared, and substitute that in for x over here. So what do we get now? Well, this is equal to 2 times the integral of u plus 1 quantity squared plus 1 multiplied times u plus 1 and divided by u times du. And now what we have to do here is we probably are going to have to multiply all this out and simplify it algebraically. So let's do that. Let's first multiply this out. So this is equal to 2 times the integral of u squared plus 2u plus 1, don't forget the plus 1 here, and that multiplied times u plus 1 divided by u times du. Okay, next step would be to go ahead and combine this two and then multiply this times that. So let's do that over here. So we have the integral, and the 2 is still outside integral sign, so we have u squared plus 2u plus 2 multiplied times u plus 1, and the whole thing divided by u times du. And multiplying out what's in the numerator there, that's equal to 2 times the integral sign, u cubed plus 2u squared plus 2u, and then multiply the 1 times all of these, that would be plus u squared plus 2u plus 2, all divided by u, du. And now we will combine like terms. So this is equal to 2 times the integral sign, u cubed plus a 2u squared plus u squared is 3u squared. A 2u plus a 2u is plus 4u plus 2, all divided by u, du. And finally, we can divide the u into the numerator. Wow, this is a lot of work, isn't it? But just stay with it. So this is equal to 2 times the integral of u squared plus 3u to the first power plus 4, because the u's cancel out, plus 2 over u du. And now we can go ahead and integrate. And of course, I need parentheses now, otherwise the du doesn't apply to all of the terms. So now we're ready to integrate. So this becomes 2 times u squared is u cubed over 3 plus 3u, that becomes 3u squared over 2 plus 4u plus 2 times, and that's 1 over u du, and of course 1 over u du is the natural log of u, so that's the natural log of u, and of course we still need a constant of integration, like that. And then don't forget we have the 2 here that needs to be multiplied through with everything, and then we can substitute every u back in for what u is equal to, which is this quantity right here. So this becomes 2/3 times, instead of u cubed, we write x to the 1/2 minus 1 cubed plus, the 2's here cancel out, so we're left with a 3u squared, and u is x to the 1/2 minus 1, and that's squared, plus 2 times 4 gives me 8, and u is equal to x to the 1/2 minus 1 plus 2 times the natural log of u, and u of course is x to the 1/2 minus 1, and then finally plus a constant of integration. And believe it or not, that is the correct answer for this particular integral. So notice that it's not always simple and straightforward, but this is really the only way to do this problem, is to go ahead and first substitute in for the denominator what this is equal to in terms of u, find the du dx, and eventually dx in terms of du. And it turns out that it does not simplify enough for us. So now we have to get rid of the x plus 1 here, and we have to get rid of the x to the 1/2. So we use this here to then come up with a form where we can substitute for x to the 1/2 in terms of u, which is right here. And then, of course, this, by squaring both sides, we can then have x substituted by u plus 1 quantity squared, then multiply everything out, divided by u, and you can then go ahead and integrate. So not a straightforward method, but at least it helps you find a way to integrate it. Sometimes integrals can be quite complicated to figure out, but it does work if you stay with it long enough. All right, very good example. And example number 12 is kind of a classic example, 1 over x times the natural log of x dx. And here when you use a method of substitution, you want to substitute natural log of x for u. So let u equal the natural log of x, which means that du dx then is equal to the derivative of that, which is 1 over x. So du is equal to 1 over x dx, and dx, I write du instead of dx. So dx is equal to x du, and we'll substitute this and this in our integral. Let's see what we get. So this is equal to the integral of 1 over x. Instead of not writing the natural log of x, we write u. And instead of dx, we write x du. And notice the x in the numerator here and the x in the denominator both cancel out. And we're left with the integral of 1 over u du. All right, and that we know how to integrate. That's a classic form. And so this is equal to the natural log of u. Of course, we need absolute value signs plus a constant of integration. And then substituting back in what u is equal to. Wow, this becomes the natural log of the natural log of x plus constant of integration. And that is the solution of this particular integral. So notice it's not that hard. Of course, you got to think about what correctly to substitute. In our last example of our current set, to show you how to integrate using method substitution, is this one right here. And right away, you see that you probably want to substitute u for the natural log of x. So let u equal the natural log of x, which means du dx is equal to 1 over x. Du is therefore equal to 1 over x dx by moving the dx over, or dx is equal to x times du. And let's substitute this and this back in the integral. That means this is equal to the integral of 3 divided by x times, instead of natural log of x, we write u to the third power. Instead of dx, we write x du. And then notice how this x and this x cancels out. And we're left with, and of course, I'm going to take the 3 outside integral sign. So this is 3 times the integral of 1 over u to the third du. Now, I'm going to take the u to the third and move it to the numerator and write it as u to the negative third. So this is equal to 3 times the integral of u to the negative 3 du. And then, of course, I know how to integrate. Excuse me. I'm going to add 1 to the exponent, divide by the new exponent. So this is equal to 3 times u to the minus 3 plus 1 over minus 3 plus 1 plus a constant of integration. So simplifying that, that is equal to 3 times u to the minus 2 over minus 2. Of course, we don't like negative exponents. I'm going to move it. Oh, and don't forget the plus c. Got to have a plus c there. And then I'm going to move the u to the minus 2 to the denominator to make that into a negative, into a positive exponent. So this is equal to minus 3 over 2 times 1 over u squared plus c. And finally, substituting back in what u is equal to, right there. And so this is equal to minus 3 over 2 times 1 over the natural log of x squared plus the constant of integration. And that's the solution of this particular integral. All right, so this was fairly straightforward. Again, make sure you remember that most likely when you have a situation like this, you want to substitute u for the natural log of x, and then the rest is fairly straightforward. Hopefully these examples help you understand how to use the method of substitution in various examples. We use some logarithms, we use some e to the x kind of functions, we use some polynomials functions, and in the future we'll do some more examples using trig functions and so forth, but at least this gives you a pretty good set to start with. So good luck with these, give them a try, take a look at the other videos, and hopefully by now you have a fairly good understanding of how to use the method of substitution to integrate.